Today, we're diving into a really profound idea. It's one of those concepts that connects things you might not think are related, like randomness, data compression, and even the very limits of what we can possibly know. And it all kicks off with a pretty simple question about two strings of numbers.
Okay, so take a look at these. On the screen, you've got two different sequences of ones and zeros, sequence A and sequence B. At first glance, you'll notice they're the exact same length.
So, which one do you think is more complex? Your gut probably tells you that sequence A is way simpler, right? But the real question is, why? Answering that, well, that gets us to the very heart of what information really is.
See, the secret isn't about the length of the string itself. It all comes down to the length of the instructions you'd need to write it out. For sequence A, that instruction is super short. Write 1 0 8 times. Easy. But for sequence B, there's no obvious pattern, no shortcut. The shortest way to describe it is basically to just write out the whole thing. Write 0 1 1 0 1 0 0 1 1 0 1 1 1 0 1 0.
And this idea, this way of measuring complexity by finding the simplest possible description, is the bedrock of a really powerful concept in computer science. It's called Kolmogorov complexity. And all it is, really, is the length of the shortest possible computer program that can generate a piece of information. You can think of it like finding the ultimate, most compact recipe to create anything, from a number to an image to an entire book. And this wasn't just some random thought experiment. It came from the mind of Andrei Kolmogorov, an absolute giant in 20th century mathematics. He was trying to figure out a way to define the amount of information in a single object without having to rely on probability. Now here's where it gets really fascinating. This one single concept elegantly ties together two ideas that we bump into all the time: compressing files and, believe it or not, true randomness. When it comes to compression, you can think of Kolmogorov complexity as a kind of physical law, like the speed of light. It's the absolute theoretical limit. No algorithm, not .zip, not .rar, nothing can ever compress a file smaller than its Kolmogorov complexity. But at the same time, it gives us the most solid definition of randomness we've ever had. A string of data is truly, genuinely random if it's completely incompressible.
Let's put that another way. If the shortest possible program for creating a sequence is just the instruction to print the sequence itself, then that sequence has no hidden patterns. There's nothing to simplify. It is, by definition, algorithmically random.
So, this seems amazing, right? We have this perfect, elegant way to measure complexity. It feels like the ultimate tool for understanding information. But there's a catch, and it's a huge, mind-bending limitation that pretty much changes everything.
I mean, this is the logical next question, isn't it? If we want to find out the complexity of something, all we have to do is find that one shortest program. How hard can that be? Well, as it turns out, it's impossible. And I don't mean it's really hard, I mean it is fundamentally, provably impossible. Kolmogorov complexity is uncomputable. There is no magic algorithm that can look at a string of data and tell you for sure what its complexity is. You can never be 100% certain that you found the shortest possible program.
And here's why it's impossible. To be absolutely sure you found the shortest program, you'd have to test every single program that's shorter than it. The problem is, some of those programs will get stuck in infinite loops. They'll just run forever and never produce an answer. This is the famous halting problem from computer science. Since you can't know ahead of time which programs will finish and which will run forever, you can never actually complete your search. So you might be thinking, okay, if we can't actually calculate it, what's the point? Is this just a useless theoretical toy? But it's not at all. Even though we can't compute it, the idea of Kolmogorov complexity is one of the most fundamental concepts in modern science, and its applications are everywhere.
The core principle that the simplest explanation is probably the best one has shaped dozens of fields. It's the inspiration behind the minimum description length principle in statistics. It pops up in network design, in quantum information theory, and even in creating truly secure communication. It's like a North Star, a guiding principle, even if we can never reach the star itself.
And this all leads us to one last, really deep question. What if a mathematical fact is so complex that its shortest proof is actually longer than the entire foundation of mathematics it's built on? Well, then that fact is essentially random. It's unprovable in that system. This idea connects directly to Gödel's incompleteness theorems, and it hints at a truly startling possibility. Maybe some things are true for no real reason at all. They might just be true by pure chance, a random, unexplainable fact of our universe. What does it mean if some truths have no reason for being true?
Now that is something to think about.